Okay, so we were looking at suffix trees. So what is a suffix tree? A suffix tree for some string. This is typically the text which you are asked to pre-process is is a trie of suffixes of t. So write down all the suffixes of the string, and then we build this tree. Okay, what is it? What is more precisely is a rooted tree with labels on the edges such that every root to leaf path corresponds to a suffix. And no two children of a node or no two edges coming out of a node has the same label. Okay, what do you mean by different starting point? Well, we'll see. And we'll have a leaf Okay, so if this is my text T, we will have, so let's see, 1, 2, 3, 4. Okay, so for another suffix technical reason, we will, just to make sure that no string is a substring of another, we add this dummy character. So, hereafter my suffix tree is going to be for this given string followed by some dummy character. So, the leaf has a label 5 indicating that this is a suffix starting at position 5. Okay. Then I'll have a B. So, this is a suffix starting at position 4, and then this B is going to be shared with this edge, because I can't have another B because of this property. Two edges of a node cannot have the same starting point. So, this B will have an A and this AB dollar will have A. Okay, so it has a leaf corresponding to every position 1, 2, 3, 4, 5, and any root to leaf corresponds to a suffix. And if you look at any node and look at the edges out of that node, they all have different labels. But so last time what we observed is that this could have potentially n square many nodes. And to bring it down to linear number of nodes, what was the optimization we did? Yeah, so just make sure that nobody has exactly one child, right. So, if you remove, for example, this node has exactly one child, so I am going to make this into one this thing and write this label AB dollar here. Okay, so anything which has, so this will be one edge, and this A and B will be combined with this. So, now you understand why I meant different starting points, because the label on the edges is not one character, but a string. So, all I want to make sure is the starting points of these strings are different when for edges coming out of a node. Okay, so this is what we will call as a suffix tree, and so some of the observations. Has n leaves, I mean including this delta. So, if assuming length of the string including the delta is n, then it has n strings, n leaves, and hence it has at most n minus 1 other nodes. And this was an exercise to show that the number of internal nodes is bounded by, I think, n minus 1, but or at most n. Okay, so what else I want to note? So, how do you actually implement such a tree, right? I mean, you have node. In this node, there are these pointers coming out with labels, and so on. For each, each edge, each pointer is going to another such node, and there is this leaf nodes. There is one ugly feature of the labels are not of the same length. So, we need to somehow do something about it in the implementation, because if you just add the edge labels, then their space is still about n square, right, because we just got rid of vertices with degree exactly one child, and that made the number of nodes to be linear, but you still have the edge labels accounting for some n square space. So, what do we do? How do we make it uniform? How do we make it linear space? So, one observation is that each edge label is actually a substring of the text. So, I just remember the starting and ending position of that substring. Okay, that's just two numbers, uniform everywhere, and that's just two numbers. So, that makes the overall space linear, right. So, I will have some I comma j where the starting and this is the end position of the label in the text. So, that makes this order n space. So, again, so what do I, how am I going to use the tree for string matching when I want to know whether some pattern P exists in the text T? What do? I start from the root node. So, let us say some P is some A, B, A, C, B. Does not matter, it could be very large. Okay, let us just make it. So, I start from here and I look for an edge with the label A, right. So, there are two ways of implementing it. One, I could have a pointer to every character of the alphabet. right, in an array. So, I know where to go to, because it's an ordered alphabet. So, if I am looking for F, I know I have to look at some 6th character and look at the 6th pointer and see if it's there. But that makes the space very large, because I might have just some 3 or 4 children, but I'm going to waste an array of 26 for this. The other option is just keep the characters here in a sorted order and do a binary search to get in there, right. So, it's like how you do in a B tree kind of thing, but that adds a log sigma time for your search. Sigma is constant, everything is fine, right. Okay. And suffix trees are really used in biological applications where you are trying to represent some genome sequences which typically has alphabet size of 4, okay, A, T, C, G or something. So, if you assume alphabet size is constant, then these issues do not matter, but you have to keep in mind that either you keep the non-empty characters here in a sorted list and do a binary search, or you have a one location for each character and then you follow through that pointer. So, I will follow through A, let us say, okay. So, A comes here, then in here I will look for C and so on, okay. So, now your search may end in any of either you may just finish off and you will reach a leaf and you still have not matched, then I know that actually you will not reach a leaf. Either you will come to an internal node and figure out that there is no edge with my next character, then in that case the pattern does not exist, or I have found and matched either at a node or in between, right. If I have a string, so if I am looking for ABA, then I will follow through and get AB, and then I come here and I starting point is A and I know I have matched it, and I sort of somewhere in the middle of the edge my search ends, okay. So, either my search, either I have nothing out of this node matching with my next character, in that case the pattern does not exist, or I have exhausted the pattern and I reach an internal node or in the middle of an edge, in that case the pattern exists, okay. And how much? So, okay, so search for P equal something, start from the root and follow the edges next character. So, no edge matching the next character, he does not exist. Our search ends with a match at an internal node or at an edge. So, then P exists, but suppose now I want to know typically all the occurrences of the pattern. Where does it exist, or where all do you have this pattern existing? So, what do we do? So, if I am looking for example for B, then I follow through here, my search is ended, pattern exists. Now, where is it ending? Well, you go to the leaves, so it is at position 4 and at position 2. Okay. So, the leaves of the subtree tell you the starting positions of the pattern. Okay, but how do we find them and how much time does it take? So, existence of the pattern, we have just spent order p time, length of the pattern, and we figured out pattern exists or not. Now, I want to output all occurrences of the pattern if it exists. So, the observation is that you have to go to the again by the properties of the suffix tree, it is clear that all the leaves, this is a prefix of some suffix, and all the leaves in the subtree where your search has ended will tell you all the positions where it is a prefix of those suffixes, and that the locations where it's appearing is given by those leaf nodes. So, what do? You just do some sort of a search, do a BFS or DFS of that subtree and collect all the leaves and output them. So, how much time would it take? Order n, which is not so nice, right? Not quite order n. You can say it's a little more tightly, which. So, suppose there are k occurrences of the pattern, then order k. Why? Because there are k leaves. How many nodes are there in the subtree? By the same argument we had here, it has order k nodes, because there are no node with one child. So, order k nodes is what you are traversing, which is reasonable, right? Because that is output size. If k is the number of occurrences and you have to tell me all where it is appearing. So, the output size itself is k, and you are spending order k time. Okay. So, to output all occurrences traverse the subtree where the search ends. So, if it ends in the middle, come to that node. And output all the leaves. So, if you are spending order k, where k is the number of occurrences. So, sometimes you may actually want to know only the number, okay. How many times it appears, I do not necessarily want to output all the positions. Then it is basically the number of leaves, but to output the number it is unreasonable to expect order k time, because the output size is just a constant here. So, what do? You could just pre-compute and store, right, because in each of the nodes, this is all part of your pre-processing. Each of the nodes uses store how many leaves are there in that node. Right? So, one thing I did not mention, which we won't do, is can be constructed in order n time. Again, a naive way of constructing a suffix tree is the way I built this tree, right. I just inserted one suffix and then I go to the next suffix and match it in the tree and insert it. That is again like an n square algorithm, but there are about 2 or 3 linear time algorithms which are slightly technical, not very hard. Just remember certain extra pointers and you can manage to construct in linear time. So, we won't discuss it. I will just assume this as a black box, that you can actually construct a suffix tree in linear time. Okay. So, So, suffix tree is very powerful. I'll tell you at least one more application. One common application is searching for a pattern in a text, which is a very important, often used application. We will see other applications, but the big problem with suffix trees is the space used by this tree. Even though it's linear, the constants are very large, and some of these big biology applications cannot really. The data sizes are very large that you can't handle this. So there has been a lot of work on reducing space. So one simple optimization again you can do is that instead of storing two characters, starting and ending position of the string here, what I will remember is only the length of the string. Okay. So we will just remember only the length. Will that help for my search? So there are lots of tricks and you can considerably save space, but is you need a starting character, of course, because that's what will help you search the length of labels on the edges. Okay, so instead of one number, instead of two numbers, I'm storing one number. But there's a problem for searching, right? How would I search? Because here I will know that so it's a the character and I'm storing this number 3. Character A can be managed because anyway it's stored. Remember, it is we are storing this pointer, so A is one of those spots stored with the node. So I just remember the length. Okay. So how will it help my search? Well, when I do my search, I'm looking for something A followed by some 3 characters. I'll follow through the A and I'll skip the 3 characters of my pattern and continue. Okay, I come here and maybe I'm looking for B and there will be some 5 it will say. So I follow through B, my pattern is 5, B, and then I skip the next 5 characters. Eventually, I suppose I end up with some node. Okay, and I have exhausted the pattern. I don't know whether I really matched my pattern or not because I skipped characters. So how can I confirm this? Right. Well, how do I know? Yeah, I go to a leaf. So go to one of the leaves here. It tells me some position. Starting point is 7. So start from a 7th position of the text. Follow through the suffix. Now match my characters, because again the property of the suffix tree is that in my text after B there is some unique set of 5 characters there in the suffix, because if there is more then I would have had another child here, right. So after B in my text there is some unique set of 5 characters. So I will now go and take my starting position from the leaf, go and verify one more time that whether my pattern matches the text. Okay, so so I double the cost of the search because I just have to do one more confirmation there, but I save space by a factor of n, because every edge had 2 numbers, now it's storing only 1 number. Okay, so there are it turns out you don't even remember the number, you can figure them out, and then what you have is just the shape of the tree, which can be compressed nicely. There are lots of other optimizations that can be done, but the important thing is that the labels of the leaves are important, because they are the ones which tell you the starting position. Okay. So let me just okay. So you can construct in linear time, search for pattern, report all occurrences, tell all occurrences. So there is there is a notion of generalized suffix tree. For a bunch of strings. Right? So, what is this? It is just a suffix tree for T1, maybe $1, T2, $2. So, concatenate all the strings. They are all over a fixed same alphabet. Concatenate all of them with delimiters. You have this one big string and build your suffix tree for that big string. Okay. And I told you can build a suffix tree in linear time, linear in the length of this text. So, it will be the sum of the lengths of this text, right. Linear in the sum of the lengths, you can build this generalized suffix tree. And yeah, so now I can ask all kind of questions, like given a string, I can ask what are all the texts in which this string appears, right. Among these k strings, my pattern P, where all does it appear? Well, again you can answer this in time proportion to the length of the pattern, because you just follow through the pattern, you get to the node, you have all these leaves, and from the leaves you figure out. Now, the leaves have position numbers as usual, but you can now think of position number as, so let us say this is of length some k1 or n1 and this is n2. So, a position n1 plus 3 means what? It is the third character of the second string, right. So, think instead of in the label, instead of writing n1 plus 3 at the leaves, you might write 3 or 2 comma 3 pair, which tells you the third character of the second string. So, when you get to the leaf, you do not have to calculate to figure out what string, what text it is appearing, right. So, you just know your pattern appears in position number 3 of your text 2, right. It may also appear in position number 7 of text 2, it may appear in position number 23 of text T5, whatever, all that, but the same search method will tell you everything. So, you can just follow through and go to all the leaves and will tell you where all your output, your text is appearing, your pattern is appearing, right. So, look at so here is a problem which is not really a string matching problem. Suppose I want to know the longest common substring of T1, T2, Tk. So, I have the string let us say there are 4 strings like this, and I want to know that string which is common to all of them and longest. Okay. So, here for example, I think an appears in all the 4 strings, and that is probably the longest. Okay. So, now I want to find something like this. This is my problem. Longest common subsequence. Okay, so suppose I want to do this even for 2 strings, not k strings, but suppose I have just 2 strings. Just imagine without thinking about suffix trees, how you would do it, right? Not that, I mean, longest common subsequence of 2 strings, we know we can use a standard dynamic programming to compute it in order mn time. M is the length of the first string and n is the length of the second string. But I don't know, you would try all possible substring. Yeah. Okay, let us see how you would use a suffix tree to compute it. Just think suffix trees and more or less the answer will pop out. So, I can construct generalized suffix tree for these case strings, right. So, you will have this big tree, and you will have these leaves, we will have this 2 characters which tells you, I comma j, that this pattern, whatever that pattern is, it appears in jth position of the ith text. So, you can compute all in linear in the total length of this string. So, now what are you looking for? Longest common, okay. How would a common substring look like? So, notice that this suffix tree actually captures all substrings, right, because you just follow from the root and go to any node, that is a substring, and that is the only way to obtain substrings, because you have captured all suffixes of every string, and a substring is a prefix of some suffix. Okay. So, what kind of substrings you are looking for? Common substrings. So, what are common substrings? Right, but from the suffix tree point of view, can you tell me what is a common substring? So, let us say this corresponds to a substring. How would I know whether it is a common substring? Leaves should have every text, right. So, I just go through the leaves, and if I have all the TIs appearing, then I know that this string is a common string. Okay. I do not know whether this is the longest common substring. Well, that is not very hard. Once you know all common substrings, you can figure out the longest in terms of length, right. So, you can do all this using some pre-computation. So, how do you want to? So, substrings are actually captured in the nodes, right. So, if you might have a string which is ending somewhere in the middle, but then you might as well go all the way up to here, because that if this substring, wherever this appears, this substring also appears. So, they correspond to the nodes. Okay. So, what do I want to store on the nodes? I mean, I want to pre-compute and store something on the nodes, so that some search of this tree, I will be able to figure out the common substring, and in particular the longest common substring. Number of texts in which it appears, right. Okay, how do I compute that first? Let us see. Yeah. So, we will not worry so much about space. So, we want to spend. So, I have constructed this big generalized suffix tree. So, now I need to know whether this node has all the strings in its leaves. Okay. I mean, I need to know this for every node. So, I start from bottom of this tree and do some sort of a post order traversal of the tree, right, and I just store the set of strings in the leaves. So, I come here, and this node I will store this set, which is all the different texts the leaves contain, and I store it as a set in this node. Okay. As I go up, I just have to take the union of all my children and put it in my node, right. So, it is just a local computation. So, I just go and do a post order traversal of the tree, post order, depth first, whatever, and store in each internal node the set I So, each internal node x, the string x appears in Ti. So, by S of x corresponding to a node, I mean concatenation of all the labels on the edges from root to that node path. Let me call that as a string x. Then, which are all the texts in which my string appears, and and I can recursively, or by a table I can compute it bottom up, and for every node I spend time proportional to the number of its children. I just take the union and put it here, and now I have this set computed for every node. Now do another breadth first search or something and figure out the nodes that contain all the sets, right, and among them pick the one which has the longest length, right. So, step 3, BFS, DFS, whatever, I think does not matter. The important thing is that you can in time proportional in linear in the number of nodes in the tree, which is order total length of the string. So, all the sets, I mean all the that is basically 1 comma 2 comma k. So, overall time is, which is sort of the best you can hope for. So, it's okay. So, many of looking for some palindromes, all kinds of things you can do by generalized suffix trees are bit more useful than just the suffix trees. You concatenate and do something. You get a lot of information about all substrings of all texts in the suffix tree. Okay. Another related data structure for string matching is suffix array. We'll get to that. So, suffix array is just a permutation of 1 to n. So, again you have a text t dollar, let's say 1 2 3 4 5 6 7. So, it is an ordered alphabet. So, let's assume that dollar is larger than every x in sigma. So, we are going to sort all the suffixes lexicographically. What do I mean by this? So, lexicographically in the dictionary order. Okay, so what are the suffixes? So, this is suffix starting at position 1. Okay, so if you want to sort them lexicographically, what would be the first suffix? Two, right? This is the one which will come first. Then you will have a and a dollar. So this is 4. Then you will have a dollar, which is 6. That's 1. Nothing else in B. That's 3. That's 5. And then you'll have a dollar. That's 7. And suffix array is basically this permutation, right? Suffix array is just 2, 4, 6, 1, 3, 5, 7. This is my suffix array for this text. That is, the suffix starting at position 2 is the smallest of all the suffixes in the lexicographic order. Suffix starting at 4 is the next smallest, and so on. So, take the sorted order of the suffixes, write down this permutation, and that's it. That's just in the suffix array. Okay. So, good thing about suffix array is that it's just one array. It, avoids all this mess about the space and pointers from suffix tree. It's just one array. But let us see how we would use it to search. Now, if I want to know whether some pattern exists, what do? We just do binary search, because it's the sorted order of the suffixes, and we want to know whether my string appears as a prefix as in one of the suffixes. So, just do binary search, because you are just given this, and you are also given the text. So, you know what 1 means, 2 means, and so on in the text. So, if I just it's a sorted order, so you just have to do binary search. If I want to know whether BAC appears, then I just go to the middle and say yes, match B, appear. It does not appear here, it goes up to this point. So, if it appears, it will be in this portion, the standard binary search, instead of searching for number, and now I am searching for the string. So, I take my BAC, compare it with this, and I realize that if it appears, it should appear in this portion, because BAC is strictly smaller than this. Then I go to the middle, compare, and I just run through my binary search, and I will know where it's appearing, if it's appearing, what are all the locations, and so on. What would be a naive running time? This is called the suffix array. Well, there are n or n plus 1 suffixes, so it will be log n comparisons, but each comparison is, in the worst case, it could be like m different character comparisons. So, if my So, it is a little extra cost in terms of the time you spend, but for this nice simple array. It turns out with an augmented array, we can improve the running time. I will come to that. How do I construct the suffix array? Okay. Again, naively, if I just want to do the way I did, write down all the suffixes, you sort. So, that is like an n log n time, but what is time? Because a comparison would be comparing this up to n characters. So, it could be like n square log n. Right, standard n log n algorithm, but each comparison costs me comparing two strings of character length up to n. Right. Do you see some relationship between suffix trees and suffix arrays? If you collect the leaves in the left to right order, but I did not pay attention to order when I was constructing suffix tree, but you could, right. How do you pay attention to the order? Yeah, so for among the children, I have this characters A, B, C, D. You just put them in that order, right? That's it. So whenever I need to create a new, when I'm inserting a suffix, when I'm creating A, then I would create it as the leftmost child because A is the smallest of these guys, right? So I will create an A here, and then maybe so. As long as you just sort the children of each node based on the first character and build your suffix tree, then the leftmost, okay, if you see it from here, the leftmost label will tell you the starting position of the smallest, lexicographically smallest suffix. The next guy would be the lexicographically second smallest. So, you build your suffix tree in linear time, and just again do some search of the tree and collect the leaves from left to right order, and you get this permutation. Okay, so that's so construct suffix tree maintaining ordered children, and then so this whole thing is, for a while this was the best way to construct suffix array in linear time. It was annoying that there is one way to do it linear time, but somehow can you go without going through suffix tree? Can you get it or some work? But yes, you can also do it without going through suffix tree. You can construct in linear time. Okay. Like I said, the big advantage with suffix array is that it's just one array. There's nothing much. Okay, and these things are really used in practice, biology and various string applications. Okay. So now I'll tell you what more we can remember. We'll remember just one more array and can improve the search time to order p plus log n. and what we store is that improving search time. By storing this LCP array where LCP of I, just one more array, longest or length of the longest common prefix So, SA is the suffix array. So, SA of I will tell you the starting position of the ith smallest suffix, right. So, SA1 is the smallest, SA2 is the second smallest and so on in the lexicographic order of all the among all the suffixes. So, now what I do is look at SAI and SAI plus 1 and look at the longest common prefix and write down the length of that. So, for example, here it would be the length of the longest common prefix would be like 3, right. Between suffix starting at position 2 and suffix starting at position 4, the length of the longest common suffix, length of the longest common prefix is 3. Between these two, the length is 1, 4 and 6. Between A and B, it's 0. Between these two, it's 0. And between these two, it's 2. And between N and $, it's 0. Yeah. So, it is of length N minus 1. So, I compute it and store it. Okay. Now, actually even this can be computed from your suffix tree really. Suffix tree is so powerful, right. So, what do I have to do? So, I just suffix tree, I have this first leaf and the second leaf and the length of the longest common prefix would be this number whatever. And then maybe if the third leaf is something like this, the length of the longest common between these two would be this number and so on. So, just by traversing the suffix tree itself in linear time, you can compute this number. So, now we will see how this is going to help in our binary search of my pattern. Okay, so, I have my suffix array which is pre-computed and stored, and I also have this longest common prefix length that's stored. Now, I mean it's the same old binary search, but now I just want to argue that you can use this LCP array and be clever about it. Okay, so we need more space here. So, we can let me write the result. So, binary search for P can be now done in okay. So, how does the binary search? So, this is my left and right, and I am just going to do my binary search. This is the middle, and I have my pattern P, right. So, my binary search has told me that my pattern is in this range at some very intermediate point, and I am going to take this pattern and compare it with this middle. Okay. What I am going to argue is that you do not have to take your pattern and compare it with starting from here based on some information you already know, which will spell it out. You can just directly start from comparing some character in the middle with some character in the middle here. Okay. So, let us see how. So, let us say suppose length of the common prefix between L and my pattern suppose is L, length of the common prefix between, suppose I know this information. I will argue that as I go along in my binary search, I can actually remember this information as well. Right. So, this is basically how much my pattern has matched. So, up to this point, let us say my pattern is matched with L and my pattern is matched with R, right. When I start, I do not know this information, but I can compute it in some order n time, right. It is just the first and the last one. I take my pattern, compare it, take my pattern, compare it with the n thing in order n time, I know this number. Okay. And I will argue that as I go along, I will know this number with L and R, whatever the range I am focusing into. Okay. And let us assume without loss of generality, L is, okay, suppose L is equal to R, what can you say? Suppose L is equal to R, it means that in my pattern, the longest common prefix with L and the pattern is L, longest common prefix with R and the pattern is same L. Now, I am going to compare in my pattern with the middle, right. What do I know already? L plus 1, R plus 1, whatever, right, because I know that since it is a sorted order of the suffixes, right, I would have also matched with this L. So, now I can start comparing with my L plus first position. I do not need to compare because I know that, see, this is a sorted order. So, if these two are actually the same, then this must, that much length here must also be the same and my pattern would have matched with that anyway. So, why bother comparing? I am going to skip and compare it with the next character. Okay, that is a easy case, right. Start from L plus first character of M and P and start comparing. Okay, let us look at the case L is greater than R, and if L is less than R, it will be analogous way we will deal with. So, suppose L is bigger than R, right. So, my pattern is matched with here, this R is here. So, now I am going to assume one more thing, which is that I also know the longest common prefix between L and R, no, also between L and M. I mean, how do I know? Well, I will tell you that you can actually compute it from this information you have stored, because here we have only stored the common prefixes of the adjacent ones, but here I am demanding that do you know the longest common prefix between L and M and R. We will assume all of this is known, we will deal with how to deal with that, I mean how do I compute it later. So, suppose now let us go through some cases. So, let us assume L is R greater than R, L is equal to R, we know how to deal with it. I think you can erase this. Okay, so case 1. L is strictly less than longest common prefix of L and M. Okay. So, what does that mean? So, this pattern and this pattern, suppose I know that they match up to this point, right. These two, they match up to this point, suppose I have pre-computed and knew it, but my pattern matches with this only up to this point. So, this L is strictly less than whatever these two guys match. Okay. Now, what can I conclude? The pattern matches with M up to the same point. Yes, exactly, and it won't match at this character also, because it did not match here, because this is the longest common prefix, and this is the increasing order of the suffixes. So, it won't match, and my pattern is here in this on the left, right. I could just proceed to the next step of the binary search without making any comparison here, right, because pattern and L and M match up to this point, but my pattern mismatches here. So, it will mismatch here, and I know that this is less than or equal to here. So, if at all my pattern exists, it will be only here, because I have moved here, right. So, now I am going to binary search in the range L and M. Without any extra comparison, I can conclude this. Agreed? Ian is not convinced. So, the pattern, okay, so L and M match up to this point. Okay, this is a sorted order of the suffixes, and I am told that, oh sorry, no, actually I want to say the other way, right, it is MR, okay. So, yeah, exactly. See, the pattern, I mean, these two characters are actually same, remember, because the pattern and this guys have matched, and this mismatches, so it will mismatch, okay. And if I have to search to the right, I better search to the right of here. So, actually what, sorry, so your confusion actually helped me, right, because the mismatch told me that I have to search to the right, but these two characters are the same. I do not need to compare, I know I will mismatch, and I know I have to search to the right of M. So, for free I get this information. Okay. L is greater than LCP, I get something similar, and what is that? So, again these two guys match up to here, but the pattern matched even more, because the pattern matched. So, these two guys are the same, but the pattern matched here. Okay. So, and I know that the character here is larger than this, but my pattern matched up to this point. So, if at all there is no way, no point I am searching here, I just have to search here. So, I just have to do binary search in the LM range. So, that means I am just moving to the next half of the binary search for free, no extra comparison, just by knowing this. It is the third case where I have to figure out and move. That means that my pattern matched up to this point, and it is exactly the point up to which these guys are the same. So, now I do not know whether I have to look here or there. So, I will start comparing here. So, I will compare with this guy, and it will tell me whether I should look here or there, because up to this point these guys are the same, exactly the same. So, when I compare with this, it will tell me whether I should go to the left or not. So, LM or by comparing okay. So I mean, if you followed, great. Otherwise, just think about it. It's not very involved what we are saying. So now I have to do two things. One, I have to analyze this algorithm, how much time it takes, and two, I have to argue that how do I know all these guys, right? I assume that I know all of this information. Okay, so let's analyze the running time now, right? Right. So the way, I mean, all the comparisons are happening here, right? You know up to this point, and then you are comparing with this. So either I have a success here or failure here when I do this L plus first character comparison, right? Let me count both types of comparisons. If I fail, then my binary search takes me to this side or that side. So how many failure comparisons will I have? One every step of the binary search, because the moment I compare and I fail, I just move left or right, right? So it's a standard binary search. So I'll have a log n many failure comparisons. If I succeed, I'm going to keep moving. My P, the L increases. I'm going to keep comparing with until the point, but the progress is that I'm matching more and more. So how much more can I succeed? Well, M, or the pattern length. So so it's order P plus log n. So now I have to just argue that the information I needed for this careful comparisons is all, either available or I can just sort of find them. Okay. I claim that this is something I can, I'll know it as I go along, because so initially L was the first suffix and R was the last suffix. I will take my pattern and do my comparison in order pattern length time and find this L and R to compute this initially, right. But as I move on, my L changes to this or R changes to this, right. The other one remains the same, L changes to this, R changes to this, and you can see that the way I am doing all these comparisons, right, in either case, that I know how much I have matched with M. That information is what I use to know, how much to proceed to the next step. Or so, I'm just going to say that compute this initially and can be maintained along the binary search. So this is how much the pattern matches with my left and the right. Okay, this is something computed initially, and as I go, I know how much I have matched with my middle element, and I can compute it, maintain it. So the next question, which requires a bit of work, is that I want this longest common prefix between L and M and M and R, because that's used to do all this computations. But what I have stored in my LCP array is just the longest common prefix between the adjacent guys. So how would I know what is the longest common prefix between L and M if I know the longest common prefix between the adjacent guys. It's the minimum of all of this, right? Right? These two suppose match up to only this point, and these two match only up to this point. There is no way this guy and this guy are going to match anything beyond this. So it just, whatever the minimum of all of it. But I can't compute this every time, minimum of, because it's a huge interval, and so what do? Pre-compute, right? Because it's all binary search, so you know exactly what binary search will ask, right? So one way to do is to just take your, binary search will do 1 to n by 2 and n by 2 plus 1 to n. This would be 1 to n by 4, so on. Eventually, 1 to 2, 2 to 3, 3 to 4, and so on, the leaves which you already computed. So take the min of these two and propagate it up to these nodes, and so it's again one order n computation. You can just sort of keep this tree with you, where you know the LCP of this entire interval. So when you need it here, it's there for you to go and pick it up. Yeah, just the min of these guys. Okay, so net, what have we argued? That suffix array, very simple data structure, because it's just an array where you can do your pattern match in p times log n, but with this augmented extra array and maybe another array of size n, you can improve the search time to order p plus log n. So if p is really larger than log n, this log n doesn't play a role. So you are getting as good a running time as what you would do in a suffix tree. Okay, I think I'll stop.